In this subtopic of thermochemistry, we're going to discuss heat of reactions and calorimetry. So let's just give you an overview about chemical energy. So chemical energy, the energy that is produced or that is gained through a chemical reaction, contributes to the internal energy of a system. Now, an internal energy of a system we're going to discuss later, but what you have to know about internal energy for now is that every system has energy, as we mentioned earlier. Internal energy is comprised of both potential and kinetic energy at the same time. Now, chemical energy is the energy associated with chemical bonds and intermolecular attractions. So it's mainly focused on the breaking of chemical bonds or on the forming of chemical bonds, as well as intermolecular attractions. As we talked earlier, the amount of heat is symbolized by Q. Now, the heat of a reaction is symbolized by Q, and reaction over here represented by Rxn at the bottom. Heat of reaction is the quantity of heat exchanged between a system and its surroundings when a chemical reaction occurs within a system at constant temperature. So it's the same as it's just the quantity of heat, but it's related to the quantity of heat exchanged with between a system and its surroundings when a chemical reaction is occurring. Now, when we're talking about chemical reactions, we're going to talk about two types of chemical reactions. We're going to talk about exothermic and endothermic reactions. Exothermic reactions, which is represented over here, this is just a thermometer, and we have in this beaker a sort of exothermic reaction. You can see here a temperature increase, or sort of a high temperature. And exothermic is a reaction that produces temperature increase in an isolated system, or in a non-isolated system gives off heat to surroundings. So remember, we can have an isolated system or we can have a non-isolated system. In an isolated system, the heat is not allowed to be exchanged with the surroundings, right? So the only way for us to visualize heat is through seeing a temperature increase in the system that we have. But in a non-isolated system in which energy can be transferred, the heat will be exchanged with the surroundings. So you're actually gonna feel the heat instead of seeing it as an increase in temperature in the system. Now, for exothermic reactions, Q reaction, so the amount of heat or energy for the reaction is negative, because heat is being given off from the system to the surroundings. On the other hand, in an endothermic reaction, endothermic reaction is a reaction that causes decrease in the temperature of the isolated system, or a gain of heat from the surroundings by a non-isolated system. So in case of endothermic, we have temperature decrease in the isolated system. But if the system is not isolated, what happens is the heat flows from the hotter to colder, right? And because we have this decrease in temperature in the system, heat will be transferred from the surroundings to the system. And of course, this happens in a non-isolated system. Let's talk now about calorimetry. Calorimetry is the science of measuring heat or heat capacity of a certain substance or a chemical reaction. Now, usually calorimetry is ideal for measuring heat evolved in a combustion reaction. So how does the calorimetry work? Well, number one, there's a sort of sophisticated type of calorimetry, which is bomb calorimetry. And then there's a different type of calorimetry, which is pretty simple, that you guys can do at home, which is called the coffee cup calorimetry, which is, as the name describes it, it's made up of a coffee cup. Now, let's talk first about the sophisticated type, which is the bomb calorimetry. As you can see here, it's an isolated system, of course. We have a steel bomb inside where the reaction occurs. We also have the wire for igniting the reaction. There's a thermometer and there's a stirrer. So how can we use the bomb calorimeter in order to find, let's say, the heat capacity of a certain substance, or the amount of heat that is produced by a chemical reaction? Well, The amount of heat for a calorimeter is of course the addition of the heat of the bomb, of the amount of heat of the bomb, and the amount of heat of water, amount of heat of wires, and all this. So everything that has to do with the calorimeter itself. And of course now we know that the heat capacity of the calorimeter ahead of time. The heat capacity of a calorimeter is the quantity of heat required to raise the temperature of the calorimeter assembly by 1 degree Celsius. And this is the equation of it. Of course, it's similar to the equations that we used earlier for quantity of heat. So the most important part to know here is that the heat capacity for a calorimeter is usually given to you. So you don't need to calculate it. On the other hand, what you need to calculate is the amount of heat that is produced by a reaction, let's say, or given off by a reaction. Now, we talked about the isolated system and how the law of conservation of energy works perfectly with the isolated system, in which Q system equals minus Q surroundings. So think of the calorimeter as a surroundings and think of the system as the reaction that's occurring. So Q of reaction is equal to minus Q of the calorimeter. Because we already have the heat capacity of the calorimeter, and we have all the information required from it, in addition to, of course, the final, the T initial and the T final, we can easily calculate the heat capacity of a reaction, or we can calculate the amount of heat that is formed by the reaction itself. The other type that I told you about is the coffee cup calorimeter, which is a simple calorimeter made up of a styrofoam coffee cup and a stopper. And there's, of course, the holes in the stopper for the thermometer and the stirrer. So again, it's an isolated system. So it works just as the bomb calorimeter, but of course, it's not as sophisticated as it. So again, Q reaction is equal to minus Q calorimeter.